Last week we talked about how X-rays, the mechanism by which the X-rays are being absorbed in the tissue. And we have established that absorption of X-rays is the major contrast in X-ray imaging. So this week we're going to talk about how we generate images from this absorption data in the real world. We'll first talk about some complications that arise in the real world, and then we'll talk about the reconstruction algorithm that is needed in the second half of this week's lectures. But first I want to start out with the underlying technique, showing some examples. This is computed tomography that we're talking about. It was invented in the early 70s. And what we're looking at here is an example of the use of computed tomography. We have a CT scan here of the abdomen. We see a lesion here before therapy and after therapy, how the lesion has disappeared. Now here's an example of a CT, early one, 1972, and you can appreciate the difference in quality of the images compared to contemporary CT with this early one. One has to really put an arrow to highlight the lesion here. This is a cranial CT, that of a head, and the lesion it's really not apparent what generated that lesion. CT was developed by Gottfried Haunsfeld. He developed a mathematical algorithm, an engineer, and Alan Cormack, a physicist. He is here, shown here, and they received the Nobel Prize for Physiology and Medicine. This is what a CT scanner looks like. I wanted to show it to you so that we have an idea what we're talking about. This is the scanner is in this enclosure here. This is the patient bed. You would lie on this patient bed, it would be lifted and then entered into this hole here where the scanning is being taking place. Here would be the head would be inserted in here. And of course, we don't want to show to the patients all the technical insight, so there's a nice cover covering up the machinery that's behind it. And now we're looking here in this video, we're looking actually at what's in the machinery. As you can see, there's something turning inside. What we're looking at here is the inside. That's this cover here is lifted. You see the cover is up here. And now you see this turning and quite a amazing noise as the machinery, the scanner, is being turned for producing the scan. So this is obviously what we don't want the patient to neither to hear nor to see. This would be intimidating and people would have much more trouble complying with the requirements of the scan. And in the lectures of this week, we will discuss the reason behind why this machine is turning, how this is used for generating images. CT is not only used for human patients, it's also used in research for animal models. Here I wanted to give you some examples. We'll first talk about the scanner itself. You can see this is now the scanner. Here's the enclosure of the scanner. Here's the person. Here's the opening. This volunteer here would be on the patient bed here and inserted into the scanner. Clearly the opening here is not adequate for the subject, for the rodent. So the scanner has been adapted for the smaller geometry. We're taking advantage of having a closer proximity of the detectors to the subject. Now here are some micro CT examples, some images, and micro CT means really CT with high spatial resolution. We're talking typically here of 50 microns spatial resolution, in plane resolution. The first image is of the abdomen. We can see here the abdomen. We see some lesions here. We have the heart here and some other organs. This is a micro CT of the rat spine. We see the spinal cord here and the discs surrounding it. This is an example of kidneys with IV contrast. We have the CT scan, and then we can see the vessels very bright. They have contrast agents in them. That's what we have discussed last week. And we can see the contrast enhances the kidneys. So this is intravenous contrast that highlights the blood flow in the kidneys. This example here is of the heart and lungs. We have the lungs here in dark. Obviously, they have low CT numbers. We have the heart here. Here's the spine. And these white dots, can you guess what they are? they are the rib cage of this rodent. And if we select the display to select the highest absorption, we are obviously going to look for high electron density, that is for calcium. This is the bone, and so this is a very nice high resolution image of the full body skeleton of a rodent in this example. The use of intravenous contrast agents can be used to depict blood vessels. The change in contrast can be extracted from the images. It's color coded in this image in red, so we see the vasculature, and this is superimposed on an image that's been thresholded for the skeleton. So we see the skeleton of the animal and the vasculature where the contrast agent has been going into. So this is a way to illustrate the architecture of the blood vessels in the animal superimposed on normal anatomy, so we can recognize where they are. Before we go to the reconstruction of the images, I want to discuss what the absorption that we've discussed last week, what that means in the real world. And we're going to mainly be talking about the linear attenuation coefficient mu here. Let's go back. We have and we'll assume here we have a tissue of thickness dx. This is a very small thickness. You can imagine it's a micron, nanometer, something like that. Just very, very small. We then have a number of photons n that come to this slice, and then we have a number of photons n minus dn that pass through the slice. So dn photons here in this example are being absorbed by this tissue layer of thickness dx. We've had talked last week about the linear attenuation coefficient, which has units of 1/centimeter, and if we assume that over the thickness of dx here, which is a good and fair assumption, we have seen that the number of photons at the position x is given by the number of photons impacting the layer n0 times e to the minus mu x. Now, if dx is very small, we can always assume that mu is constant in x. The measurement for which we want to reconstruct is a two-dimensional image of the linear attenuation coefficient. So I'll write this here as the function mu of x and y. But what is actually measured is the number of photons that arrive in the detector. So how is the link between those two measurements? Let's look at that. Well, it's actually a simple logarithm. So the logarithm of the measured photons divided by the photons impacting the layer, that is equal to minus mu x. And since we know x, we can, in this simple example, we can infer the linear attenuation coefficient. This here is the example for a homogeneous object with thickness x here. So we'll have assumed here that this is x for this example. Now, contrast is well defined for monochromatic X-rays. We have the linear attenuation coefficient for a certain photon energy in kiloelectron-volt. That is a well-defined parameter, and so we get very well-defined contrast. But we have seen that the linear attenuation coefficient depends on the photon energy, it depends on the atomic number, and it depends on the electron density. This has some consequences in real life, and one of the consequences is beam hardening, and the other one is depth-dependent contrast. And this you can imagine in the following way. When the photons arrive at the tissue, they have a certain spectrum of energy, and this spectrum of energy has different absorption. So the linear attenuation coefficient depends on the energy of the photon E mu. And so we have a higher absorption typically at the lower energies. So that means that the energies are being removed, and the energy of the photons that pass deeper into tissue, the average energy increases. And that's what's called beam hardening. And that is a consequence, because the mu is dependent on the photon energy, we are getting a depth-dependent contrast. So let's look at this in the real world, and we will first focus on the energy spectrum of an X-ray tube, what this really looks like. So this is the relative output on the y-axis. On the x-axis we have the photon energy in kiloelectron-volt, and we have the distribution of the density of the photons for a given energy window plotted here. What we have First is the Bremsstrahlung continuum. Remember, we had talked 2 weeks ago how X-rays are being generated. They're generated primarily by Bremsstrahlung, and we cannot predict exactly what the energy, precise energy is. So there is a continuum, a distribution of photon energies that are given. We have also characteristic X-rays, that is when we remove an inner shell electron, so-called radiation spikes, or characteristic X-rays or fluorescent X-rays. And this is the interaction with orbital electrons. And here we have the K alpha 1, alpha 2, and the K beta lines here for tungsten. What we do know, there is one fundamental constant that is fixed, and that is the maximum photon energy. This photon energy here in this example is 90 kiloelectron volt. It is given by the voltage applied on the X-ray tube across the anode and cathode. In this case, it was 90 kilovolts. So this is a fundamental limit. It is defined by the operator. We can set it in the scanner, but this is the maximum that we have. We cannot have a photon energy that's higher than that. It comes simply from the fact that this photon energy is when an electron that impacts the anode target loses all its energy at once into a single photon. So what we have is the total intensity, that is total number of photons that are being produced, is the integral of this function here from 0 to infinity of the relative output here. That's the intensity as a function of the energy integrated over the energy. This is a complex function. We don't really have a good mathematical or physical model to model it. So what we are looking at is to characterize it in a simpler way. And the way this is done is to define a effective photon energy, E effective. It kind of corresponds to the medium or median energy of the photons that are seen by the subject. So the effective energy in this example would possibly be something like this in from the X-rays that are leaving the X-ray tube. Now here's a term that I need to introduce, that I'd like to introduce, that is the term of soft X-rays. They are soft because they have low energy. They're called soft because they don't penetrate very deep into the tissue. And in contrast, we have the hard X-rays. They are high energy, they are more penetrating, and that's why they are called hard X-rays. Now, if we think about the process of Bremsstrahlung, the minimal energy of a photon that is produced is close to zero. So in theory, it's possible to produce very soft X-rays with an X-ray tube, but that's not what we see here in this graph. We see the energy drop off here to zero at around 10 keV. What we do have is a filtering of the instrument. Remember, the X-rays are produced in vacuum in the X-ray tube. We have a glass there where the X-rays are being allowed to pass towards the subject. And that glass filters the very soft X-rays and nothing goes through. So we're having this instrument filtering here from the glass, for example, that removes photons. And one consequence of that is that the effective energy is actually shifted to higher energies. So the overall X-ray spectrum, or the X-rays that impact the patient, are becoming harder. So this increase in effective energy is filtering of soft X-rays is done by the instrument, and this removal will lead to an X-ray spectrum that's shifted to higher energies and therefore harder X-rays. So what is the consequence of energy-dependent absorption? So we have a similar consequence to what we just discussed with the instrument in the tissue. Let's look at the linear attenuation coefficient here. We have the X-ray energy from 0 to 100 kiloelectron volt on the x-axis, and we have a logarithmic scale of the linear attenuation coefficient on the y-axis. In the ranges that we are concerned for X-ray imaging, for CT imaging, we're dealing only with a photoelectric effect and the Compton effect. Now, as we can see, at low energies, we have a stronger dominance of the photoelectric effect. So the linear attenuation coefficient increases quite substantially at low energies. Now, what does this mean for the real world? Let's look what we would have ideally. Ideally, we would have monochromatic X-rays. The monochromatic X-rays, we would be at this position. We would have a uniform absorption of the X-ray. The photon energy does not change. But in reality, we have polychromatic multi-energetic X-rays. So the consequence is that we have the absorption is not uniform with photon energy. Here, clearly, the linear attenuation coefficient is not uniform, so it changes. The contrast, therefore, changes with large objects and with depth. Another consequence is we have excessive radiation dose to superficial tissue. So let's talk about the first consequence, contrast changes with large objects. We have, as the X-rays impact, let's say we have a distribution of X-ray energies over this range, we have first a removal of the intensity at the low photon energy. So we have a contribution of the photoelectric effect to the contrast mechanism. As the X-ray beam traverses the tissue, these photons are preferentially removed, and so we have an increasing contribution of Compton effect to the absorption of X-rays. So we have a shift from photoelectric effect to Compton effect. Obviously, if you imagine that this is skin here, then we are looking here at a removal of the photons primarily in the superficial tissue, skin, fat, and so on, and therefore a higher radiation dose to these tissues. How can we mitigate this effect? So the solution is actually to reduce the intensity for photon intensity for soft X-rays, that is for low energies in this range here. We'd like to have not too much energy here, and this can be, for example, done with inserting a 3 mm aluminum plate, which eliminates 90% of the 20 keV photons.